We present the sample complexity of automated mechanism design. In this work, we study combinatorial or multi-item, multi-bidder auctions, and we are concerned with designing revenue-maximizing auctions. In the combinatorial setting, the amount a bidder values a bundle of goods may not equal the sum of the amounts she values the individual items in that bundle. Thus, combinatorial auctions allow the bidders to express their complex preferences. Any auction designer must determine two functions: the allocation function, who will get what based on the bids, and the payment function, what will the bidders pay based on the bids and based on the allocation. The standard assumption in mechanism design is that the bidder's valuations are drawn from some distribution D, and the mechanism designer has perfect knowledge of this distribution. In fact, the allocation and the payment function rules often depend explicitly on this distribution. This poses two major design challenges. First, in the combinatorial setting, the support of the distribution might be doubly exponential. Second, where would this perfect description of the distribution come from anyways? In this work, we relax this common assumption in the following model. We fix a class of auctions to learn over using samples from the distribution. In other words, the auction designer receives a set of samples from an unknown distribution over bidders' valuations, and he somehow uses these samples to come up with an auction to run. Implicit in this process is the assumption that an auction that performs well on the sample will also perform well at the time of the auction. In other words, it will perform well in expectation over the distribution. As one might expect, the bigger the sample is, the better it represents the distribution. Therefore, what we really want to know is, how big should the sample be in order to ensure that with high probability, for all auctions in our class, average revenue on the sample is epsilon close to expected revenue on the distribution. We answer this question by using and extending techniques from learning theory for a rich hierarchy of combinatorial auction classes that are common in the automated mechanism design literature.